So this is signal processing with web audio. I'm Jordan Santell. And so, quick introduction. With the web audio, it's a relatively new API. All major browsers support this, except IE, but they just announced this week that they will support this in the next version, which is awesome. So this audio API is a modular routing API used for manipulating audio. It's used in games, synthesizers, and audio production tools. So what is the signal processing component of this? So signal processing is the theory of manipulating and analyzing a signal. In the case of web audio, the signal is an audio buffer, so just a giant array of data. So quick about me. I love this GIF. So I work for Mozilla on the SDK team for the SDK for add-ons and developer tools, and also the web audio developer tools. So the web audio API, it is a route-based audio API for processing audio signals, and it's constructed as a directed acyclic graph. So the audio flows from source nodes to the destination node, and along the way it gets either transformed or analyzed and manipulated. And all the audio nodes are created within a sandbox called the AudioContext. All nodes must live within a context, and the context decides things like what's the sample rate of this whole graph. So it can be a little confusing because it's unlike most other new web APIs. So there are 4 node types. These aren't official. These are just ways to classify them to better understand the API. So there are source nodes, and so source nodes emit sound. They're the origin of some kind of signal. We can make source nodes out of things like the WebRTC audio stream, HTML audio element, an oscillator, and what's the last one? Something else. And so this is where the origin of sound. So the sound travels through the directed graph, and it could possibly be either transformed or analyzed. So a transformation audio node would be something like delay, filter, compression, something that will transform the audio signal so it sounds differently. An analyzation node, it doesn't affect the actual signal, it just lets us better interpret it and get information about it. So we would do that for something like an audio visualization. And finally, we have a destination node. And anything that we want to hear must ultimately arrive at the destination. So in this example, we have 3 sources, and they could be anything really. And it goes through some filtering, distortion, panning, reverb, and ultimately a compressor. And the destination node in the Web Audio API is a abstraction for our sound card. So if we have a source node and we want to hear it, whether it's a MP3 file or whatever, it ultimately has to flow into the destination node so we can actually hear it. So if this still doesn't make sense, here's a Viking metal band. So you go to a concert, the guitarist is setting up, and you think of the guitar as a source node. This is where the sound originates. The signal travels from the guitar through the cable into this is a Viking metal band, so they're going to have a lot of distortion. So to transform the clean guitar signal, it goes into a distortion pedal, makes it heavy, much louder, things like that. It transforms the signal. And then ultimately from the distortion pedal will go into an amplifier so we can actually perceive it and it'll be a good concert. Another way to think about this flow, this audio context flow, is similar to middleware in routing. So like Express.js middleware. You can think of a request as a source. So when someone requests some file from a server, that's the origin of this process. And then ultimately you could go through several pieces of middleware, wherein this middleware can transform or analyze the request throughout. So if you want to, have a middleware check, make sure the user's logged in or something for some resource, then the middleware would analyze that and determine whether it should proceed. And ultimately, you get a response, which is the final destination for that. So a really simple example. First, we create the audio context. Again, all nodes and everything must live within an audio context, and you have to have the context to create these nodes as well. So we instantiate an audio context and create an oscillator and a gain node. To use the node types I explained before, an oscillator is a source node, so it creates for example, a sine wave. So that's where the sound originates, and it can travel through a gain node, and gain is a fancy word for how loud something is. So this signal originates from an oscillator, travels through a gain node, since we connected our oscillator to our gain node, and then the gain node connected to the destination so we can actually hear it. And then we have to start the oscillator. So here's an example. Make sure we're quiet. So it's a really annoying sound. So here's an example of the audio tools in Firefox, which just draws the context graph so we can see what node is connected to which node, and we can also edit things. So in the last slide, we saw an oscillator node that's connected to the gain node, which is connected to the destination at the far right. The other two nodes, the analyzer and script processor, are just for the demos to display the time domain data. So that's obviously a sine wave, very fast. So oscillators create these tones with periodic cycles. So and they're created by some kind of equation. So a sine wave is created by the mathematical sine function. And all these waves are periodic waves, so they're repeated patterns. So let me make sure. There's other type of oscillators other than sine wave. We can have triangle. And it's named that way because it looks like a triangle. Square wave. Is that too loud? Excellent. And my favorite, sawtooth. And you can see how these waves are named because they actually look like the object that they were named after. So if those familiar with electronica music or synthesizers, or if you ever played a Game Boy, a lot of these sounds are the foundation of any synthesizer. Synthesizers use these basic waveforms to construct more abstract and complex shapes. And we'll do a little bit of that in a bit. So we can change the type. So right now it's a sawtooth. And we can also change the frequency. So the frequency is measured in hertz. And it's a unit that represents how many times per second this periodic wave cycles. So at 440 hertz, this shape is repeated 440 times per second. And that's what we perceive as pitch. So 440 is a concert A4. So if I drop this an octave to 220, we can see we actually perceive a lower pitch, and you can see the cycles are a little bit slower. It's still 220 times a second, but if we drop this to something inaudible, like below 20 hertz, 5, let's say, we can actually perceive that because we're not robots. Somewhere there's like a dog. Right, yeah. We're scaring all the animals right now. So I mean, that's a really terrible sound. No one wants to listen to pure sine waves. All the dogs are angry right now. So we can manipulate these signals in a bunch of different ways. So one technique is amplitude modulation, in which we want to change. An amplitude is so how high the signal is, and which we perceive as volume. So if we want a really loud sine wave, we would have really large cycles. If we want quiet sine wave, it would be a really subtle wave. So what we can do is, in the previous example, we connected one audio node to another audio node, but we can also connect audio nodes, which again is just this pure signal, to an audio parameter. So in amplitude modulation, so we have a carrier signal, which this is our pitch, same thing we did in the last one. So let's assume this is a 440 sine wave. We can also have a modulating sine wave signal that affects some other property in the audio context. So this modulating sine wave signal is much lower frequency than the carrier signal. So we can use this modulating sine wave signal to tween between a loud sound and a soft sound. So if we combine these two signals or have the modulating sine wave signal affect the subsequent gain, we can see in the last image, as the modulating sine wave signal approaches -1, the carrier signal gets much quieter. So to implement something like this, similar to the previous one, we have an oscillator, our carrier signal, connected to our gain node, and our gain node is connected to our context destination, just like we had in the last example. We also have another oscillator, our modulator, that's connected to the gain node's gain audio parameter. So as the modulator goes between 1 and -1, it'll tween the volume of our signal. So it's a little bit more interesting. So it'll sound something like I'm going to make a lot of weird sounds throughout this. So it'll be like a whoa, 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 because we're pulsating the volume. So in this graph, we have our oscillator again, gain node connected to our destination node. But this oscillator down here, this is our modulating signal. So right now, it's only a frequency of 5. So this is only repeating 5 times per second. So this means the carrier signal is going to go between full gain and no gain 5 times per second. So if we change the modulating signal, we can change how often this pattern is repeated. So sorry about that. So we change this to 1. So only once per second is this gain changing. And we can see it actually being visualized as the volume decreases, there's no activity in the time domain data. And we can do this with other waves other than the sine wave. So we got a sawtooth wave as our carrier signal, which sounds like a broken Game Boy. So we can use amplitude modulation to make things a little bit more interesting because no one wants to hear pure sine tones. Another thing we do is frequency modulation, where instead of modifying the amplitude or the volume, we're modifying the actual pitch or frequency of the carrier signal. So same idea as amplitude modulation. So our modulating sine wave signal is changing the frequency or how often the cycle of the carrier signal is repeating. So we see in this example as the modulating sine wave approaches -1, the frequency of the carrier signal increases. So the distance between each cycle is lessened, which we perceive as pitch. So if we're going between a lower pitch and a higher pitch in a synthesizer, we'll get some like weird 80s sci-fi like woo, woo, woo. Been waiting to do that. So I think I did it better, but this sounded pretty good. So this is pretty much the same example, except we're, let me go to the code real quick. So same thing, except instead of connecting our modulating oscillator into our gain node's audio parameter, we're connecting it to the carrier's frequency. So as the modulating signal goes up and down, so does the carrier's frequency. And as you've seen in this sweet example, I have an album just of that. And so the only difference thing here is that our modulating oscillator is also going into a gain node just to increase the change. So if we change the modulating oscillator's gain node to 1, it's not that much of a difference. It's not changing the frequency too much. But if we crank that up to 1,000, we get some weird stuff going on. And we see, like, again, this is modulating the frequency. So we see the sine wave, the carrier signal, crushing together when it's a higher frequency and expanding when it's a lower frequency. So we see this kind of like breathing effect. So again, you're not going to listen to, that still doesn't sound good. But again, this is the foundation of, any kind of like electronic music synthesis. And so notice that we're also using really low frequencies for the modulating signal. This is 2 hertz. Humans can hear between 20-ish hertz and like 20,000 hertz. So we can't really perceive this, this signal, even though because it's affecting it. So if you increase the modulating signal to something that we can perceive, things get weird. So let's make this. So the carrier signal is 440, and if we make the modulating signal 100, so that's like a bass note on a bass guitar. So we get this weird modulation effect. So like, if you want to pretend you're a Dalek, you would do something like this. And so the reason why we use low frequencies for modulating is so we can't perceive it. Maybe we just want a subtle effect, like use often like tremolo, phasing, vibrato. We don't want to perceive that. So this is called a LFO, not the 90s boy band, but a low frequency oscillator. So we don't perceive it. We just we have some kind of pattern, so we can like repeat amplitude modulation or frequency modulation or some other effect. So, and we can also modulate other audio parameters, not just frequency and amplitude. So we can plug this in, we can pipe an oscillator into a filter, a delay node, anything that we want. So we can get more interesting things. Otherwise we just sound like, you know, Game Boys. So that sounds really cool in here. So for this example, so again, similar to the other ones, except right now we have 2 oscillators, 2 carrier signals, one at 40 hertz, a sawtooth, and a square wave at 80 hertz. And those are octaves apart, so it doesn't sound awful. Going into a filter node, and a filter, you know, think of like an array filter function. Filtering is kind of pretty much equalizing. So right now this filter node, a biquad filter, is a low pass type. So it has a frequency value, and right now it's at 500. So this means that any frequency higher than 500 is significantly reduced. So we only really hear the notes below 500. And the modulation that we're performing here, we have, again, an oscillator node at 1 hertz. So the modulation will happen once per second. And that's being pumped into the biquad filter's frequency property. So what is being, you know, animated or tweened or modulated is the low-pass filter frequency. So as the sine wave continues, we're going between only allowing just the low frequencies, which humans have a hard time perceiving, so it sounds quieter than higher frequencies, into allowing more and more frequencies and then oscillating back. So that's what we hear here. So it's just cycling over, letting lower frequencies, only lower frequencies, and letting more and more frequencies in, and then going back. So sorry. So in this example, same thing. Slightly different properties for the oscillator node. Except we also have 2 modulating signals at this point. One is controlling the filter node, just as in the last one. So 0.5 hertz, so this is happening once every 2 seconds. And a gain node to increase it. And then we have an oscillator node that's controlling the gain. So we're also doing the filter modulation as well as amplitude modulation. Okay, so and we can also, so again, this isn't, you know, this is just like a simple example of some, you know, synthesis that can be performed. And we can hook this up to a, you know, a touch interface like a keyboard or something and trigger whether or not these notes stop and start and deal with sustain if a user holds in a note and things like that. And we can also just automate everything and just compose a song that requires no human input. So we can do things like, what's that? So, and this again, we're just dealing with, I'm a composer. So we're just dealing with, we just started with 2 oscillator nodes. One's a sawtooth, one's a square wave. And so we came from this like Game Boy sound into something that could possibly be in a song or an album or a concert because we just made dubstep. So, thanks everyone. So I'm Jay Santell on GitHub and Twitter. Bug me if you have any questions about web audio stuff or the Firefox Dev Tools for Audio. It's coming out in Firefox 32. And still have no idea what we're doing with it completely, but any feedback would be awesome so we can make it better, so we can have more game developers using the Web Audio API, synthesizer makers, and audio production engineers. So thanks, guys.